cause light to diverge. Did I show you? It doesn't look like I've shown like that. So for example here, if I have this converging lens, if I have light rays that come in like this, a converging lens will cause the light rays to come together. And then a diverging lens, if I have light rays that come into a diverging lens, that will cause the light rays to go apart. And so that's why we call them converging and diverging lenses. And have I shown you? I did show you all the other types of lenses, right? Biconcave, biconvex, plano-concave, plano-convex. These two are biconvex and biconcave. We'll deal primarily with these, and these are the most common lenses, these two. Let me show you just a little bit about how to draw rays for this. So remember we had talked about wavefront, wave diagrams, and ray diagrams. When we're dealing with lenses, it's going to be very useful for us to think about rays. So light traveling in these straight line paths, we'll just imagine like a single ray. And but first I wanted to find the focal point. I think I might have already defined the focal point in one way. Is that correct? Let me look back up here. No, I have not. All right, so we can define the focal point in two different ways. First, the focal point is 1/2 the center of curvature. And then second, the focal point is the point where light rays focus. Excuse me, where parallel light rays focus. Where parallel light rays focus. So if I consider a convex lens, that's a converging lens. If this is my center of curvature on either side of this, so this is C, the center of curvature, then the focal point is at a point halfway between the lens and the center of curvature. So we can define it in that way just based on the geometry. These lenses are cut out of a big sphere, right? I can imagine this extending out into a big circle. This is the radius of that sphere. This is 1/2 the radius. So the focal point is 1/2 the radius. I can also imagine if I have parallel light rays, and remember parallel light rays, as we talked about with sound as well, they come from an object that's very nearby or very far away. Parallel light rays. Very, very far away. Like the sun, for example. When we're here from the sun, the light rays coming from the sun are very far, are basically parallel. But it doesn't have to be that far away. Like light rays that are coming from the back of the room are also parallel by the time they reach me, basically. All right, so these parallel light rays will focus at the focal point. All right? At the focal point, they'll focus. That's where they cross. I want to show you some rays and how we create images with lenses. These are called ray tracing diagrams or ray diagrams. You're not going to have to draw ray diagrams, but it's useful when we're talking about the eye to understand some basics about how these ray diagrams work. Morning, ladies. We can draw, say, imagine that I have a convex lens, and I'll deal primarily with the convex lens because that's what we have in our eye. Our eye basically consists of one convex lens. A little more complicated than that, but not terribly more so. So I have a convex lens. I can draw a couple of rays. First, I'm going to draw an axis that goes along the center of the lens. I can draw an object right here. So I have an object. And then these are my focal points. This is my focal point on the left side and my focal point on the right side. Remember, I have two curved surfaces, so I have two focal points because they come out of two circular or two spheres, two spherical surfaces. I can draw one ray that goes parallel to the axis, like that, and then it goes through the focal point. That's how we define the focal point. Right? I can draw another ray that goes through the focal point, like that, and then it goes parallel to the axis. Right, so I'll call this ray number 1, and and I'll call this ray number 2. Parallel to the axis through the focal point, and then the second ray is basically the reverse of that, through the focal point, parallel to the axis. Now, where my image is, this is my object, right here. My image, then, is going to be over here. This is my image. My rays originate from the top of my object, sort of normal way that we draw these. My rays originate here, and so where they cross is going to be the top of the object. Now you can draw rays from the entire part of the object, and then you'll find that the image is oriented in this way. But wherever the rays cross, if they cross below this axis, then you know that your image is going to be inverted. If they cross above the axis, you know that it's going to be upright. For the human eye, this is the scenario that we have. You get an image that's produced that looks like this on the back of your retina, or on your retina. This is a particular type of image. Remember we talked about virtual and real images? This is a real image. I think we've already covered that, right? Yeah. No, that's next. Okay, I'm sorry. This type of image is called a real image. Right, the one below the axis. This is not an image. This is an object. That's whatever the thing is, right? A dog or whatever you're looking at. This is your image, and it is a real image. It's called a real image because it can be projected onto a screen. Any image that can be projected onto a screen is a real image. So for example, this image that's up here is created by the lens and the projector. This is a real image. There's another type of image called a virtual image that we also encounter a lot. A virtual image, while you can see it, it cannot be projected onto a screen. All right, so it can be seen, but not projected onto a screen. For example, the type of images produced by a flat mirror is a virtual image. And so most of the images that we see are virtual images. The type of image produced by a flat mirror is a virtual image. You can see it, right? You can see the image in a screen or in on a flat mirror, but you can't project it onto a screen. What you see in the mirror, you can never project onto a screen. However, a real image can be projected onto a screen. A virtual image, later we'll talk about the distance. This distance from the lens to the image. In the very next section, we'll talk about this distance. This is called the image distance. And this distance is called the object distance. Right, the image distance and the object distance. The image distance for a real image is positive. Oh, by the way, the variables that we'll use for this are DO, the object, the distance to the object, and this is called DI. If you ever see this elsewhere, sometimes they're listed as P and Q is also a common thing, but I won't use that in this course. But those are just the variables that we'll use, DO and DI. For a virtual image, the image distance is negative. So here, DI is negative. And over here, for a real image, DI is positive. For virtual image, we just say that the image distance is negative. Let's see, I'm going to plug this in. Find that outlet. Is that going to blind y'all? I'll try to turn it off soon. This is an object, and I have a lens on which I can produce a real image. I'll pass this around in just a minute, but this is a convex lens. all right? And if I stand far enough back, I can produce an image of this on this paper. So I'm going to take it, and I can produce an image of the light bulb on the paper. And I'll pass this around so you can try it, but you'll see that the light bulb is upside down in the image, just like we drew over here. So I'm standing some distance away from there. That is outside of the focal point, and it's producing a real image. You can also do this with the lights on the top of the ceiling. You can produce a real image. Actually, that might be better for y'all to do. Just as you come around, you can produce an image on this screen. You'll see it, Elise? Yeah. You can produce an image. It's actually a pretty sharp image where you can actually see the ridges in the light fixture. So I'll pass this around and you can practice with it. But this is an actual real image that you're seeing, not a virtual image. And this type of lens is a convex lens. Let me show you one other thing, though, before you do this. This is also can be used as a magnifying glass. And so if you hold your hand in front of it like this, then you can see a bigger part of your hand, right? It's a magnifying glass. You ever used magnifying glasses before? Also for people with certain eye conditions, gosh, I forget, is it nearsighted or farsighted? I think it's farsighted. You use convex lenses, and if you hold it in front of your eye, it'll make your eye look bigger. Does my eye look bigger? Does it? Does it? Okay, we'll talk about this in just a bit. Is it like movie big? Like in, I haven't seen. You can't tell. Okay. All right. Well, anyway, so you can use it as a magnifying glass too. Now, the image produced by a magnifying glass, however, you cannot project onto a screen. And so that is a virtual image. So convex lenses can produce both virtual and real images. And the difference is where the object is with relation to the focal point. I'm going to write this down in just a second. But convex lenses can produce both virtual and real images. If my object is outside of the focal point, it produces a real image, like the lamp. But if my object is inside the focal point, like the magnifying glass, that's a virtual image. Let me write that down and I'll pass this around. So you can produce both virtual and real images. I'm just going to turn this off because it's going to blind me and everybody else. But when you're passing around, you can look at the light fixtures, produce an image of the light fixtures. Let me just write what I just said. Convex lenses produce both virtual and real images, or can produce virtual and real images. For the virtual, if this is my lens, these are my focal points, the object is right there. So it's inside the focal point. That's like the magnifying glass. You have to hold the object up close to your magnifying glass for it to produce this bigger image. All right, for real, here's my lens, here's my focal point. The object is outside of the focal point. Convex lenses produce both virtual and real images. For virtual, the object is inside the focal point. For real images, the object is outside the focal point. Concave lenses, on the other hand, we're not going to deal with concave lenses very much, but we'll sort of mention them because they're used for far-sighted people. I get these mixed up all the time. We'll cover it in just a second. But they're used in eyeglasses sometimes. Concave lenses only produce virtual images. I want to pass around something else. This is a cool little real image, actually. I think it's kind of cool. These are mirrors, but spherical mirrors act a lot like spherical lenses just because of their geometry and the way that you would draw rays. So these are two mirrors. This type of mirror is called a concave mirror, but it's really a lot like the convex lens in the way that it treats light. And so it can produce a real image. This is like your shaving mirror, by the way. Right, you have or a makeup mirror or whatever. And what does this do to you if you look at it? It magnifies you, right? So you can hold it up close to your face and you'll see your face like really big and like all the, dirt and pores and all that stuff. If you want to see that this early in the morning. All right, can y'all see yourselves in this, some of you? How do you look, Ashley? You're upside down, right? So if you hold this far enough away, about like this, you look upside down. So I'll pass it around and you can hold it up close to you and you look upright. And if you hold it back, you look upside down. All right? I also want you to, it's going to have this is a little pig. And you can put it right here. By putting two mirrors together, you can look at it and it actually produces a type of real image. This is actually a little bit more complicated than this real image because you're not projecting it onto a screen. But it's a type of real image and it's a hologram. So you can, kids love this, by the way, if y'all ever get one of these. Because you can see it. It's like right there. And you want to grab it, but it's just an image. It's a little hologram. All right, so I'll pass this around, and you can feel free to take it apart and look at your different images, your upside down image, and then your upright, blown up image. Okay, let's look again at the focal length. We're not going to do the lens maker's equation. All right, so no lens maker's equation. It was a small portion anyway. But I do want to look at focal length. The lens maker's equation was in this section on focal length. What's that? Just the part on the lens maker's equation, yeah. All right, so on the, and that's under focal length, but we are going to look at focal length. Optometrists and scientists talk about the strength of a lens. And this strength of a lens refers to how much it bends light. And that is a lens that bends light a whole lot will be a very strong lens. And a lens that doesn't bend light as much will be a not as strong lens. All right, so the strength just refers to how much it bends light. Let me show you a couple of lenses. So imagine that I have this lens, which is sort of long and skinny. And then I have this lens, just sort of fatter in the middle. All right, these two lenses are going to bend light in a different way. This lens, because of its shape, will bend light not as much. So its light will focus far away from the lens. In comparison, this lens, which is short and fat, will bend light a lot. All right, so which of these is stronger? The one on the left or the one on the right? The one on the right has a higher strength, right? Its strength, it's a higher strength. We call this the power, by the way. So if I call these A and B, the power of lens B, and this is the term that we use, the power of lens B is bigger than A because it bends light more. We can calculate the power. The power is equal to 1 over the focal length. The focal length of lens A is big in comparison to the focal length of lens B. Oh, actually, that's not right. I'm sorry. Let me redraw that. These are parallel rays, right? So the focal point will be at the point where the rays focus. So the focal point, or the focal length of lens A is that distance, but the focal length of lens B is that distance. So lens B, which has a higher strength or a higher power, has a shorter focal length. And it's because of this inverse relationship. Since f is small, P is big. Lens B has a short focal length, so a high power. Power, you've probably heard the units for this before, especially if you wear glasses. Power is measured in diopters. And it's just the inverse of the focal length. However, be very careful because the focal length has to be in its SI units. And we don't usually use the focal length in its SI units, but it has to be in this case, and that's in meters. If I give you a problem where you have to calculate the power and I give you the focal length, I'll give it to you in the SI units. But if you ever see this elsewhere, usually the focal length, like of your eyeglasses, is given in centimeters, not in meters. And so you'd have to convert that into meters if you wanted to know the power of your lens. Actually, when they talk about your eyeglass lens, they usually talk about the power, not the focal length anyway. Okay? Have y'all heard of power, diopters for glasses before, or contact lenses? Yeah, well, it's true for contact lenses as well. They have a diopter. Okay, let's look at the thin lens equation. Actually, let's see, I think I have a few questions for you. I can get it to come up. And I will send out these questions soon so that you'll have them to prepare for the exam with the correct answers. See where we left off last time. I think we left off when light enters a medium, it slows down. Does anybody verify that? I think this was our last one. Okay, so a virtual image. Oh goodness, I don't have my thing up in a second. A virtual image can be projected onto a screen, has a negative image distance, has no magnification, or cannot be seen. Just a second, my clicker's not up yet. Okay, virtual image is which of these? Okay. All right, so a few more seconds. I'll stop at 45. Okay, very good. B is the right answer. You can see a virtual image. It's a real, I mean, it's not a real image, but it is an actual image that you can see, but you can't project it onto a screen. It's like what you see in the flat mirror, like in that Poltergeist movie. Have y'all seen that movie? Come to the light. Have y'all seen that from the 80s? Yeah, was her name? Caroline. Caroline, come to the light. All right, concave lenses produce what type of image? Remember, concave lenses are those that look like they're caving in. This is a concave lens. What type of image does a concave lens produce? Only real, only virtual, or can it produce real or virtual images? All right, so a few more seconds. I'll stop at 50 or 52, let's say. All right, very good. Concave lenses only produce virtual images, only virtual. But, oh, never mind. Convex lenses produce what type of image? A convex lens looks like this. This is also called a converging lens. Only real, only virtual, or real or virtual? Stop at 30 seconds. 30 seconds. Very good. Remember, there are a couple scenarios where you can produce a virtual or real image. It's dependent upon the focal length. If your object is outside the focal length, it produces a real image. If your object is inside the focal point, it produces a virtual image. Oh, and by the way, I didn't mention this, but when I say focal length or focal point, those are basically the same things. I use them interchangeably. Technically, focal length is the distance between the focal point and the lens, and then focal length is that distance. So, but we'll use them interchangeably. A convex lens has a focal length of plus 0.5 meters. What is its power? I'm going to send these out to y'all when we finish them. So, all right, just a few more seconds. I'll stop at 52. Okay, very good. The power is just the inverse of the focal point. So power equals 1 over plus 0.5, 1 over a half. That's equal to 2 diopters. Sometimes with your lenses, if your lenses in your glasses, if they're not convex, they're concave, they'll say that it has a negative power, right? So in that case, your focal length is actually negative. Don't be terribly concerned about that now, but if you see that you have a negative power, that's what it means, that you're not using a convex lens, you're using a concave lens. The focal length is equal to which of these? Half the center of curvature, the point where parallel rays focus, or the center of curvature, or some combination of those. Let's stop at 50. Okay, 1 and 2 is correct. So A is correct. Geometrically, we define it as half the center of curvature, but the way it treats light is the place where parallel rays focus. So there are two different ways that we can define them, either by the geometry or where parallel light rays focus. And I think one more. Yeah. A virtual image has a blank image distance, positive, negative, or 0. We've had one very similar to this already. All right, just a few more seconds. I'll stop at 35. Okay, excellent work. So B is the right answer. Virtual image has a negative image distance. Yeah, Tori? Yeah, focal length and focal point are the same. I can use them interchangeably. As I said, technically, focal length is the distance from the focal point to the lens, but you can use them interchangeably. All right? All right, guys. Let's look at the human eye. So we're really concerned with the eye and how it works, which is why we're dealing with this. But in order to look at that, we first want to give you the lens equation, the thin lens equation. This just describes how light travels through a thin lens. When I say thin lens, I mean the convex lenses that we're dealing with. So something with a focal length that's fairly large, not a small focal length, a really short, fat one. So the thin lens equation looks like this. 1 over the focal length equals 1 over the image distance plus 1 over the object distance. And you can use this to deal with any type of lens, whether it be a convex or concave. You can also use it to calculate your image and object distance for various spherical mirrors. Like that's a concave mirror or a convex mirror like you have in a security mirror. We're not going to do any of the calculations, but it's useful to look at in terms of the human eye because, well, for most instruments, like cameras, for example, microscopes, telescopes, for most instruments, if the object distance changes, actually, if DO changes, that's the object distance, you adjust DI, the image distance, to focus the image. All right. So, for example, with a camera, if you look at something far away, then you have your camera set up in a particular way. But then if you focus on something that's close up, then the lens will actually adjust to either move further away from the film or from the CCD or whatever it may be, or closer to the film. Right. So for most instruments, if the object distance changes, you adjust the image distance to focus the image. Similarly, like with a microscope, you can move the platform up and down or change the eyepiece. Likewise, in a telescope, you can do that as well. Though with a telescope, your DO is always infinite because you're looking at very far objects. However, with the eye, and the eye is different in this way, and it's actually quite remarkable. For the eye, the image distance is fixed. It doesn't change. Because if we look at a cross-section of the eye, and the eye looks something like this, it's a ball, basically, and this has a convex lens, the image is always going to be back here. All right, so the image distance, DI, doesn't change, right? Because the shape of your eyeball doesn't change. That would be too difficult. And so the eye does this remarkable thing where instead of changing the image distance, the focal length of the lens will change. So when DO changes, when the object distance changes, the focal length changes to focus the image. I can't think of any man-made instrument that does this. There might be in some special case, but nothing that we use really in real life would actually cause the focal length of the lens to change. Because it's very difficult. I mean, you have to have a lens that is flexible, and that's very difficult to make. It's a lot easier to make glass lenses. Y'all done with the pig? Yeah, that's all. They don't do the same thing. They don't change the focal length. Now, you can change out your lenses and give yourself a new focal length, and that's sort of the same, but your actual lenses don't change their focal length. Instead, they move back and forth and change the image distance. So that's not the same. They change the image distance, not the focal length. But here, and as we'll see with the human eye, I'm sure you've seen this in anatomy, but there are muscles that actually adjust the shape of the lens in the eye that will cause the focal length to either increase or decrease, depending on whether you're looking at something far away or something nearby. That's pretty remarkable. And it's also an instrument that lasts for like 80 years for the most part. And, you know, we don't really have any instrument that lasts for 80 years. I mean, it's obsolete in a few years, right? But the eye stays with you. And you have problems, of course, but for the most part, your eye stays with you and continues to function well. Y'all like the pig? Is it cool? Like I said, kids love this. Like, they just freak out. It's like, oh, I can't get it. Little squeals of laughter. All right. Okay, so if I think about this in terms of the thin lens equation, I'm going to write the thin lens equation in a different form. That is 1 over di equals 1 over f minus 1 over do. All right, so this doesn't change. 1 over di doesn't change. And so this difference between 1 over f and 1 over the object distance has to remain constant. So if do decreases, you know, that means the object is near. The focal length has to change in response to that. Is the focal length going to increase or decrease? It's going to decrease as well. I know it looks like it's an inverse relationship, but everything's inverted. So it's like it's a direct relationship. So if do decreases, that means the object is near. The focal length has to decrease too. If do increases, that means, you know, it's far away. The focal length increases. So if I'm looking at something far away, like the back of the room, and then I want to look at something nearby, on my finger or whatever, my focal length will have to decrease. Let me show you that. I'm going to draw a little diagram, a couple of ray diagrams like I showed you before with those two rays, and you can see how the focal length of the eye will change. Can I come down from here? All right. So here's two eyes, cross-section of the eye. There's our convex lens. And I know that my image has to form back here, because that image distance is fixed. Here's another one. Now, for the first one, my object is really far away. All right, so I have a light ray that comes in, is parallel to the axis, and it's going to focus there. All right. And in fact, all my light rays coming from this, by the time they reach the lens, are going to be parallel to the axis. So actually, let me just erase this. So imagine that I have an object that is really far away. And so all of my light rays are going to focus at the focal point. Because if I have an object that's very far away, an infinite distance away, by the time the light rays reach the eye, those light rays are going to be parallel to the axis. All right, so for this eye, the one up top, my focal length is that length, that distance. For something far away, the focal length is the diameter of the eyeball. For faraway objects, the focal length equals the diameter of the eyeball. For nearby objects, on the other hand, we have an object that's right here. My focal length is going to be shorter. I'm going to go and draw the focal points here and here. And my rays will look like this. I have one ray that will come in. Then we're parallel to the axis, and then it goes through the focal point, like that. Then I can have another ray that goes through the focal point, and then parallel to the axis. This is the same ray diagram that I drew before. And so my image will appear like that. Images, by the way, on your eyeball, you probably know this, but they always appear inverted on the retina. And then that image is taken to the brain via the optic nerve, and it flips it. And then so on the back of my retina, there's an image of what you see right now that's upside down. But then that image is flipped so that you can see it. So in your mind, you see it right side up. They have glasses that you can buy, actually. Have y'all heard of these that flip everything upside down? They're like for fun or whatever. I'm not sure what kind of fun that would be. But it takes everything that you see and it flips it upside down so that you see an upside down image of everything. But after you wear them for a while, you get used to it. And then eventually your brain will actually flip that image right back up again. Isn't that cool? I think it takes a while, I understand. I've never tried them, but I think it's kind of neat. Okay, let's see. Let's look at the anatomy of the eye. Oh, so one other thing, by the way, actually. So you have these muscles that push on this lens and can make it either make it skinnier or fatter in the middle, or it can stretch it out. Those are called your ciliary body. In this case, if you're looking at something that's close up, the lens is going to have a shorter focal length. It's going to have to be wider in the middle, right? To shorten the focal length, the lens has to become wider in the middle. No, it pushes in. So like if it were to pull out, it would stretch it thin. But in order to do this, it has to push the lens in. You follow what I mean? Yeah. Think about a marshmallow, right? If you push a marshmallow, it sort of bulges out on the side. The same thing happens here. You push it in, and it bulges out in the middle, and that shortens that focal length. Okay, yeah, let's look at the anatomy of the eye. I sent out a diagram last time, and I'll pull it up in just a minute. But you'll need to know the basic parts of the eye. Many of you probably already know this. But as we talked about, the eye is a sphere, basically a sphere. It can be slightly elongated or slightly squished, and that will lead to some problems that we'll talk about in just a bit. It's filled with clear fluids. We talked about this in the chapter back on pressure, right? Remember the intraocular pressure? We talked about these fluids, the vitreous humor and the aqueous humor. And it also contains the lens. I'll lay these out in more detail, but just sort of. The lens and the ciliary body. The ciliary body is actually what changes the shape of the lens. There are 3 layers in the wall of the eye. Actually, let me pull up this image first to sort of give you an overview. Okay, yeah, so it's a sphere. This is the lens that's right here. This is the cornea. The lens and the cornea together will act as our convex lens. And in fact, we'll say this later, but the cornea actually causes most of the refraction in the eye. So most of the bending of light occurs right here as light enters. There's the pupil, there's the iris. We'll get to those in just a bit. This is the ciliary body. These are these muscles that can squish down this thing and make it with a shorter focal length, or stretch it out and make it have a longer focal length for looking at things that are far away. And then back here we have the detection part. Well, these are the three sections: the sclera, the choroid, and the retina. The retina is mostly on the back of the eyeball, and this detects the light. Remember, there are rods and cones on the retina that detect, what is it? Rods are black and white? Is that right? Yeah, rods are black and white, cones are for color. And then it goes through the optic nerve to the brain. It said there are 3 layers to the wall of the eye. They're shown right here: the sclera, the choroid, and the retina. Can I come away from this? There's the outside layer, excuse me, or the fibrous layer. This consists of the sclera. That's the white part, and the cornea. So this covers the outside of the eye. The cornea, of course, is clear. That's where the light comes into your eye, and it's part of the lens system of the eye. The white part is a protective part of the eye. You have muscles that are attached to the sclera that can cause you to move your eyes back and forth. Bless you. And then second layer, you have the vascular layer. This consists of the choroid, the ciliary body, and the iris. The choroid contains blood vessels. It brings nutrients to the eye. Keeps it healthy. The ciliary body is a group of muscles. These change the shape of the lens. And then, of course, the iris is the colored part of your eye. It's basically an aperture. Your book doesn't go into this very much, but they do mention spherical aberrations. There's this aberrations that we face with cameras, and these are called spherical aberrations. And the iris is there to get rid of spherical aberrations. It's also there to limit the amount of light that comes into the eye. By the way, did you know that your eye can detect just like a few photons, like just few little particles of light? And it can also detect light that's very strong. And we don't really have an instrument that does anything like that. Like, we have instruments that can detect a few photons, and then we have instruments that can detect stronger light, but nothing that can detect that entire range, which is pretty fascinating. But anyway, spherical aberrations occur because if you have light rays that come onto one part of a lens, they will focus at a particular point. And just because of the spherical nature of the lens, if you have light rays that come onto another part of the lens, they're going to focus at a slightly different part, at a different focal point. This occurs in cameras a lot. It occurs in any spherical lens. There's not a real easy way to well, there is an easy way, but apart from it, there's not an easy way to get rid of it. But the easy way, which is what the eye does, is to just block out those outer edges of the lens. So what the iris does is it just comes along and it blocks out these rays, so it only allows these rays to come into the central part of the lens. Cameras do this as well. They have an aperture over the lens that blocks out light from all the other parts of from the lens. If your eye didn't have this, things would just look fuzzy all the time, because you would have different focal points of light. You would have light focusing here and light focusing here, and you wouldn't get a clear image on your retina. So that's fairly fascinating. A very simple way to deal with spherical aberrations in the eye. All right, so the iris prevents spherical aberration. And then finally, the sensory layer. Can I come down from here? All right, the sensory layer, which, as I said, can detect just a handful of photons, or it can detect very strong light without saturating the detector. It's the innermost layer, and it contains the retina. And the retina converts light to an electrical signal. And then that signal is sent to the brain via the optic nerve, and it's converted into an image in your mind. It just converts light to an electrical signal. Within the retina, we have rods and cones. These are two types of detectors within the retina. The rods are for low light, black and white situations. Or rather, they're for low light. They're sensitive to low amounts of light, but they're not sensitive to color. And that's why in the evening time, like at dusk, things don't look like they really have color, right? Like just before the sun goes down, you look at trees or whatever, they don't look green and brown. They just sort of look gray or black. It's because these rods are being activated, and so you can't really detect the colors. Cones, on the other hand, require lots of light. So for bright light situations, and they are sensitive to color. Did y'all study this in anatomy? We did have a question. Yeah. I read that your cones, you have 3 sets of cones, and it's red, blue, and green. And that doesn't make sense to me why it would be red, blue, and green, the colors of your cones. Anybody know the answer? Like, I would think they would be the primary colors, which are what? Red, blue, and yellow, right, are the primary colors? Does anybody know the answer to that? Yeah. Mm-hmm. Uh-huh. Okay, so you can get all the colors from RBG. Okay. Okay. Uh-huh. That's the cyan, magenta, whatever, whatever. Yeah, okay. All right. Okay, well, I guess, so it's dependent upon just sort of how we detect colors, I guess. Sounds like what you're saying. Okay. Anyway, so the cones are for bright light, and they are sensitive to color. So when you're outside, you can see color, but not in low light situations. It looks like everything's just sort of black and white or grayish. Let's see. Was that me? Okay. It sounded like me. Um, okay, so rods and cones. The retina, just a second, I'll give you a quiz. Let me finish this little topic. The retina also contains the fovea and the optic disc. The fovea is the back of the eyeball, and has a high concentration of rods and cones. All right. That's like where most of your images are formed, on the back of your retina, your best images. And so you want the most detectors there that you can have. And then the optic disc is where the optic nerve is attached to the retina. That's where the optic nerve is attached to the retina. There are no cones here. So this is like a blind spot on your retina. If you look on that image, actually let me pull it back up again. It's right here. This is this optic disc, and it's just where that nerve attaches to the retina and carries that electrical signal to the brain. And so there's no detectors there, and so you get this blind spot there, but your brain actually fills it in. So even though like you're not seeing a portion of it, it fills in sort of the rest of the image. It's a small portion of your retina, mind you, but it interpolates between what's not there and what is there, so that it doesn't look like a blind spot. All right, we'll stop there. You know, I'm not sure that we'll get to that assessment next time. If that's the case, then we'll just do it after the fourth exam on the time of the final. Okay? Is that clear? But go ahead and bring a Scantron next time. You know, I mean, you'll need one eventually anyway. And bring your N number as well. We'll try to get to it next time. So I'm going to give you a quiz now. Y'all sort of spread out, if you will.